Induce EMF in a rotating coil. So we have a bar magnet, which is this is the north pole and this is the south pole, meaning that we are creating a uniform magnetic field. Okay, and we consider a rectangular coil of n turn, each of area A, which is being rotated with a constant angular velocity omega in that uniform magnetic field. Okay, when the vector of area A is at angle theta to the magnetic field, the magnetic flux through each turn of the coil is given that, okay, from the basic formula of magnetic flux, okay, B A cos theta, and theta is actually the angular displacement, and we know that the theta is equal to omega t. So we can derive the equation of magnetic flux equal to BA cos omega t. By applying the equation of Faraday's law, which has a turn n turns, okay, thus the induced EMF, okay, is given by, okay, induced EMF equal to negative number of turn time to the rate of change of magnetic flux. Okay, from the previous equation, okay, so magnetic flux, okay, is actually the differentiate of BA cos omega t. Okay, and then we have to factorize the quantity which is constant in this equation, okay, which is number of turn, magnetic field, and the cross-sectional area. Okay, so we have to differentiate of cos omega t. Okay, when we differentiate of cos omega t, the equation is actually induced EMF equal to NBA omega sine omega t, where t is actually the time taken. So the induced EMF is maximum when the sine omega t equal to 1. So the induced EMF maximum is actually equal to NBA omega. From the previous equation of 5.11, which is induced EMF equal to NBA omega sine omega t, and we know that the theta or angular displacement is equal to omega t. So the equation also can be written as induced EMF equal to NBA omega sine omega t, where theta is actually angle between vector A and vector B. So as the conclusion, when we have a coil rotating with constant angular velocity in a uniform magnetic field, okay, the coil will produce a sinusoidally alternating EMF because the orientation of the coil is changing in terms of time. Okay, this phenomena was the important part in the development of the electric generator or dynamo. Example 5.9. A rectangular coil of 100 turns has a dimension of 10 cm times 15 cm. It rotates at a constant angular velocity of 200 rpm in a uniform magnetic field of flux density 5 Tesla. Calculate the maximum EMF produced by the coil, and B, the induced EMF at the instant when the plane of the coil makes an angle of 38 degrees to the magnetic field. First, okay, we can calculate the area of the rectangular coil, which is the dimension is already given. Okay, therefore the area is 1.5 times power of negative 2 meter square. And then in that question, we are already given you the angular velocity, which is omega, okay, 200 rpm. So first we have to convert revolution per minute into radian per second. So 200 revolution per minute, Okay, we cancel the minute. Okay, so this is the second. Okay, 1 minute is actually equal to 60 seconds. Okay, revolution, and this is the radian. Okay, 1 revolution equal to 2 pi radian. Therefore, 200 RPM is actually equal to 20.9 radian per second. To calculate the maximum induced EMF produced by the coil, from the formula of maximum EMF, we know that equal to NBA omega. Okay, so by substitution value, number of turn is 100 turns, and the magnetic field is 5 Tesla, and the area is 1.5 power of negative 2, and the omega is 20.9. Therefore, the induced EMF maximum is actually equal to 157 volt. For question B, we have to calculate the induced EMF when the plane of the coil rotates at angle of 38 degree to the magnetic field. So first, we have to illustrate the position of magnetic field. For example, pointed to the right. Okay, and we have the plane which is at an angle of 38 degree to the magnetic field. So from this figure, we know that the direction of theta should be measured from the vector of area plane to the B. So this is the vector of area plane, meaning that the theta in this case is actually equal to 90 degree minus with 38 degree, or 52 degree. And induced EMF for the rotating coil, we know that the formula is NBA omega sine theta. Okay, and number of turn is 100. B5. Okay, area is 1.5 power of negative 2. Okay, and the omega 20.9. Okay, and the theta is 52 degree. Okay, so the answer is 124 volt. Self-inductance. Consider we have a solenoid which is connected to a battery, switch S, and a variable resistor R. When the switch S is closed, a current I begins to flow in the solenoid. Okay, the current produces a magnetic field whose field line through the solenoid and generate the magnetic flux linkage. When the current flows through the solenoid, we can determine the direction of the pull through the solenoid by refer to the right-hand grip rule. When the current is pointed downwards, therefore, this end of the solenoid, okay, by refer to the direction of thumb, is based on north pole, and this side of the end of solenoid will act as a south pole. If the resistance of the variable resistor change, thus the current flow in the solenoid also change, then so too does magnetic flux linkage. According to the Faraday's law, an EMF has to be induced in the solenoid itself since the flux linkage change. Okay, by refer to the Lenz's law, the induced EMF opposes the change that has induced it and known as a back EMF. Okay, for the current I increase, we know that the B through the solenoid will increase, and for the initial pull, okay, which is present as the red color, so we have the north pole and this end as the south pole. But when the current I increase, the magnetic field increase. Therefore, by using the Lenz's law, we know that we have to reduce the flux linkage through the solenoid. Therefore, the direction of pull bar magnet of the solenoid, okay, will be in the opposite direction, which is present as the blue color. So, this end will be a south pole and at this end is the north pole. Therefore, we know that the direction of current is actually in opposite direction as the initial current. So we can conclude that when the direction of the induced EMF is in the opposite direction of the current I. According to the Faraday's law, an EMF has to be induced in the solenoid itself since the flux linkage change. Okay, by referring to the Lenz's law, the induced EMF opposes the change that has induced it and known as a back EMF. Okay, for the current I increase, we know that the B through the solenoid will increase, and for the initial pole, okay, which is present as the red color, so we have the north pole and this end as the south pole. But when the current I increase, the magnetic field increase. Therefore, by using the Lenz's law, we know that we have to reduce the flux linkage through the solenoid. Therefore, the direction of pull bar magnet of the solenoid, okay, will be in the opposite direction, which is present as the blue color. So this end will be a south pole, and at this end is the north pole. Therefore, we know that the direction of current is actually in opposite direction as the initial current. So we can conclude that when the direction of the induced EMF is in the opposite direction of the current I. So the self-inductance, which is present as the symbol of capital L. First, we have the formulas for the self-inductance based on the process of self-induction. We know that the induced EMF generate based on the change of current. So that's why the first formula for self-inductance is L equal to negative EMF per di dt, or ratio of the self-induced or the back EMF to the rate of change of current in the coil. Okay, so this is the first formula. And for second formula, we know that the self-inductance, okay, through the inductor, we have the flux linkage. Okay, so the self-inductance L for the second formula is actually number of turn times with the magnetic flux divided by current in the coil. Or we can also rewrite the equation in terms of magnetic flux linkage per current. And the last formula used for self-inductance is based on the structure of inductance. Okay, which is for the coil, the formula of self-inductance is mu naught n square A divided by 2R. And the R is referred to the radius of the coil. For the solenoid, formula used for self-inductors is actually mu naught n square A over L. Okay, so based on this formula, we know that the self-inductance, okay, depends on the value of size and shape of the coil, and then number of turn, okay, and the permeability of the medium in the coil, mu. So in the circuit, okay, we have an inductor, so which is the symbol, okay, of inductor, and is used to store energy in the form of magnetic field. And the formula that we use to calculate the energy stored in the inductor is actually equal to U half L I square. Inductance times with the current squared. Okay, and the unit for the energy must be joule. Mutual induction. Consider two circular closed-packed coils near each other and sharing a common central axis as shown in the figure. Okay, when a current I1 flow in coil 1 produced by the battery The current I1 produce a magnetic field line inside it. Okay, as shown in the figure. And this field line also pass through coil 2. If the current I1 changes with time, the magnetic flux through coil 1 and 2 will change with time simultaneously. Due to the change of magnetic flux through coil 2, an EMF is induced in coil 2. This is in accordance to the Faraday's law of induction. In other words, a change of current in one coil, for example, coil 1, leads to the production of an EMF in a second coil, meaning that the second coil, which is magnetically linked to the first coil. Okay, so this is process that we know as a mutual induction. So, mutual induction is defined as the process of producing an induced EMF in one coil due to the change of current in another coil. At the same time, the self-induction occurs in a coil 1 since the magnetic flux through it change. Mutual inductance M. Consider we have coil 1 with number of turn N1 and coil 2 with number of turn N2. If the current I1 in coil 1 change, the magnetic flux through coil 2 will change with time and an induced EMF will occur in coil 2, where EMF2 is directly proportional to the negative rate of change of current in coil 1. Therefore, the equation of EMF2 equal to negative M12 time with the rate of change of current in coil 1. An induced EMF in coil 1, EMF1, we got the EMF1 equal to negative M21 time with the rate of change of current in coil 2, where we know that M12 is actually equal to M21 and M is actually a mutual inductance, and mutual inductance is a scalar quantity and the unit for the mutual inductance is Henry, or the symbol is capital H. So, we can conclude that mutual inductance is defined as ratio of induced EMF in coil to the rate of change of current in another coil. And from the Faraday's law for the coil 2, thus we got that another formula for mutual inductance is V equal to magnetic flux linkage through coil 2 to current in coil 1, or magnetic flux linkage in coil 1 to the current in coil 2. Mutual inductance for two solenoid. Consider we have a long solenoid with length L and cross-sectional area A is closely wound with number of turn N1. And we have another coil of secondary coil with number of turn N2 turns around it at its center as shown in figure. When a current I1 in the primary coil or N1, it's produce a magnetic field B1, and we know that the formula is mu naught N1 I1 per L, length of the solenoid. And the magnetic flux through the coil 1, solenoid 1, is equal to B1A cos theta. Okay, and when we substitute the B1, which is equal to mu naught N1 I1 per L, we got the formula for flux 1 equal to mu naught N1 I1 A per L. And when there is no magnetic flux linkage, therefore we got that flux through coil 1 is actually equal to the flux through coil 2. If the current I1 change, an EMF is induced in the secondary coil. Therefore, the mutual inductance occurs and given by mutual inductance by 1 on coil 2 is actually equal to the flux linkage through coil 2 per current in coil 1. When we substitute the equation of flux 2, which is we know that equal to the flux 1, we got the formula of mutual inductance by coil 1 on coil 2 is actually equal to mu naught N1 N2 A per length of the solenoid. Example 5.13. We have a current of 3 ampere flows in coil C and is produced a magnetic flux of 0.75 Weber in it. When a coil D is moved near to coil C, a flux of 0.25 Weber is produced in coil D. If coil C has 1000 turns and coil D has 5000 turns, A. Calculate self-inductance of coil C and the energy stored in C before D is moved near to it. B. Calculate the mutual inductance of the coils. And C. If the current in C decreasing uniformly from 3 ampere to 0 in 0.25 second, calculate the induced EMF in coil D. First, let we list all the information given based on coil C and coil D. So from the statement, we know that the current flow through coil C is 3 ampere and the flux in coil C is 0.75 Weber, where the number of turns of C is 1000 turns. Meanwhile, for coil D, we know that the flux through coil D is 0.25 Weber with number of turns is 5000 turns. So to calculate the self-inductance of coil C, meaning that we have to refer to the all quantity given based on coil C. So we have the three formula for self-inductance, but the most suitable formula that we should choose to calculate the self-inductance of coil C is based on flux linkage. Since we already have the current flow through the coil and we also have the flux through the same coil. So by using the formula flux linkage, okay, we can calculate the formula for self-inductance of coil C, okay, where L equal to flux linkage of coil C divided by current to the same coil. So we got the number of turns is 1000 and the flux is 0.75 and the current flow through the same coil equal to 3. Therefore, the self-inductance for coil C is 250 Henry. To calculate the energy stored in C, so we know that formula for energy stored is actually equal to half self-inductance times with the square of current. So that from we already calculate the self-inductance for coil C and we also have the current that flow through the same coil. Therefore, by substitution the value, okay, half self-inductance is 250 and the current that flow through the coil C is 3 ampere, meaning that we got the energy stored in the coil C is 1125 joule. To calculate the mutual inductance of the coil, okay, so first we have to recall the formula for the mutual inductance, which is we have three formula for mutual inductance, which is the first one is based on the induced EMF, okay, and the second one is based on the flux linkage, and the third one is based on the structure of the solenoid or the coil. meaning that for the most suitable formula that we should use in this situation, or based on the information given, okay, we have to use the second equation. Okay, since we already have the flux through coil and we also have the current flows. Okay, so by refer to the formula of M equal to flux linkage in coil D to the current flow through coil C. Okay, because for mutual inductance, okay, we have to pair the situation given. If the flux linkage based on coil D, meaning that the current should be on coil C. So we substitute that the number of turn of coil D is 5000 and the flux through the coil D is 0.25 and the current that flow through coil C is 3 ampere. So we got the mutual inductance for this coil C and D is actually equal to 417 Henry. For question C, okay, if the current in C decreasing uniformly from 3 ampere to 0 in 0.25 second, calculate the induced EMF in coil D. So for mutual inductance, we have one formula that refers to the induced EMF, which is based on the definition of mutual inductance. Okay, ratio of induced EMF in a coil, okay, to the rate of change of current in another coil. So meaning that when we are going to calculate the induced EMF in D, so we have to refer to the change of current in another coil, which is coil C. Okay, so from the formula, EMF D equal to the negative M rate of change of current. Okay, so since we are going to calculate in D, the change of current should be in C. And the change of current or rate of change of current is already given, where the final current is 0 and the initial current is 3 ampere. And the time taken, okay, is actually 0.25 second. Okay, for mutual inductance, we already calculate in part B, which is 417. Therefore, the induced EMF, okay, for coil D is equal to 5004 volt.